a few minutes late because of the previous class was take longer time. Okay, so today we change topics. So last week we talked about money and financial mathematics, or some very, very basic about financial mathematics. This week, maybe this lecture and next Tuesday, because Friday we don't have lecture, we are going to talk about logic. So the purpose of talking about logic is the language of mathematics, because I cannot teach any mathematical course without using logic. So you'll see the importance. Okay, so the outline, the plan of today is I'll say something about why we want to spend time on logic, right? The relation between mathematics and logic. And then we talk about some logical facts. So we'll study something called connectives. So those things are like and or which put two sentences together, right? So it's connecting two statements. So they are called logical connectives. So we are going to study the truth table of things related to those connectives. And then we'll do one or two examples about how to use logic to derive something. Right? So we are going to talk about logical rules and how to use the rules to get some conclusion. Okay. These things are very, very basic, and if you have taken this CS 1231 or something, this is like a Disney version. Okay. Okay. By the way, my research field is mathematical logic, so I will be happy if you have questions about these parts, because certainly I cannot. This is not a mathematical course. I cannot go very, very detailed. So if you have questions, please ask me during the break or after the class. Okay. So now I want to start the topic by asking you some questions, right? So we are studying mathematics, right? So this general education module is called Living with Mathematics. Now mathematics is a very special discipline, right? So mathematics is different from experimental sciences. I mean, it's different from biology, different from physics, different from chemistry, although we are all in the faculty of science. So why? What are the differences? So here, actually, it is related to philosophy of mathematics. Right? So in philosophy of mathematics, there are two typical questions. One is about, is this question one? It's about ontology. Ontology is a big word about what is there. What is the world made of? Okay. What the things exist in the world? Those things are okay. Okay. So now the first question is, what are the mathematical objects? Do they exist? Well, you think, I don't know. Okay, there are so many people, right? What do you think? Do you think mathematical object exists? Like number 10? No. Okay, so then what is mathematics about? Right? If there's no such object, what are we learning? Living with mathematics is like living with something which is totally, it doesn't exist. So this is an interesting question. Okay. So that's one of the biggest questions in the field of philosophy of math. The other one is, what is the nature of mathematical truth? If I talk about, biological truth, right? I say this animal has certain thing, certain property, or then I can do experiment, or I can somehow film or catch the animal and then check my theory whether it's correct. But as someone already said, mathematical object doesn't exist. Now, when I say something is true, and I say some mathematical truth, what do I mean? How do I check? And also, how do we ever get mathematical knowledge if it doesn't exist? We cannot observe, we cannot test, we cannot. Then how do you learn? But obviously, we learned a lot of mathematics, right? In JC, in SOC, or in engineering, you learn lots of mathematics. So how do you learn it? So these are questions. Okay. By the way, I don't have answer, and in philosophy department, people are still debating. So it's not as laughable or as shallow as you think of. It's actually very, very interesting, very, very deep questions. Okay. There are lots of things, there are books written and lots of things behind these. Okay, but my purpose is not to answer those two questions, but I want to say the importance of logic in mathematics. Okay, so now I want to say, no matter how you think of mathematical objects, there's one thing is true. I think you should believe that mathematical theorems, that is the things we have proven or whatever, seems infallible. It's always true, right? For engineering, if a bridge collapses, you will have doubts about material, you will doubt about workers, whether they follow the plan. But usually, I don't think you will doubt about the mathematical formulas involved in the design, right? So it seems that comparing to experimental sciences, mathematics may be more correct or has lesser chance to fail, to be wrong, right? So I hope you agree with me on this. Okay. Now, what gives mathematics this how to say, this property, right? Okay, you may have other explanations. One possible explanation is, okay, because those mathematical theorems follows logic, right? So what I mean by follow logic, so it's like when you establish a theorem, you have to go through something called a proof. So what is a proof? The proof is like a logical chain, right? So you start from something very simple, and then you do things step by step. Each step you follow something called logical rule. You follow certain logical rule, then you can go to very complicated argument, but at every small step is logical, right? So in the end, you reach your target, which is the theorem you want to prove. Let me repeat it. So what is a theorem? The theorem, you start from something called axioms. Axiom means something obviously true. And then you follow the logical rules step by step. In the end, you reach the conclusion. Now, okay, the logical rule, everybody, if you see the rule, you definitely believe the rule preserves truth. After I give you the specific examples of rules I'm going to apply, I'm sure you'll agree with me. It's so intuitive, so clear that the logical rule will preserve truth. So if you start from something called axiom, which you assume is true, then you follow the rules which preserve the truth. So the truth will follow through the proof all the way to the end, right? So that's why the theorem is true. It's because of the starting point is true, and when you follow the proof steps, the truth was preserved. So in the end, it's still true. Right? So this is the one possible explanation. So now here, well, obviously here in the statement, I already use the so-called logic. logical chain, right? Or I use some words which involves logic, right? So we want to take a closer look at these terms. So what exactly are the logical chains, and what are the rules, and so on and so forth. Okay, so that's the introduction. Now the first thing, so logic is a study of these kind of things. The first thing we want to study is the connectives. Okay, well, in the introduction, I already showed we want to determine the truth of mathematical statements, right? So, but many mathematical statements are complicated. It's a long statement, right? It's a very complicated. So they are compound statements, right? This has nothing to do with compound interest, but they consist of lots of short sentences and then somehow combined by some connectives, right? But those complicated statements can be decomposed into simpler ones. We'll see examples. So you can decompose them into simpler ones. Now eventually you decompose, you get shorter and shorter, simpler and simpler statement. In the end, you have to stop because right, there are only that many words you can cut. Right? So in the end, you eventually hit something we call it atomic formula, atomic statement. Atomic is like atom; you cannot split anymore. Right? Okay. Now, the compound statement have grammatic structures. So this part of logic actually is related to linguistics, right? So so the statement follows certain rules. So the rules, so they were built by using connectives, and there's another thing called quantifier, which next week we are going to introduce. So this week, today's lecture is only about connectives. So let's study them one by one. Today we study connective. Next week we study quantifiers. Okay, so I didn't give you any example of statements. Now here I'm going to give you a few. By the way, all these examples are mathematical examples. So in real life, the language was richer, and you can have more fun of the daily life language. Mathematical language is a bit boring, but they are more accurate. So since we are studying mathematics, I will skip the fun. I'll just talk about a boring mathematical statement. Okay. Okay, so these things are examples of mathematical statement. The red part is the so-called connectives I'm going to look at in the next few slides. Okay, so first statement. So this is a funny number. This is a very long number. I don't want to read. So this number, the claim is not a perfect square. I will explain what is perfect square later. Right? So it's some number has some property. Is a perfect square. The next statement says pi. Pi is a ratio, of the circle. The length of the circle is the diameters, right? So the claim is this pi is bigger than 3 and less than 4. So it's pi is bigger than 3 and pi is less than 4. Okay. The third example is either this number. Okay, at first I want to choose 2020, but 2020 is so obvious not a prime, right? So I choose 2021. Okay. So this number, 2021, either this number is a prime number. Again, I will define what a prime number is. So either this number has this property, it's called a prime number, or it has some other property. It is divisible. You can use a number to divide. Right? it is divisible by some number not exceeding 45. So it's a statement. It's a statement about number, this particular number, 2021. So it's the compound statement has two parts, right? Connected by this or either or. Okay. And then it's quite often to see a statement like this. It is of the structure if-then. If something happened, then something else, right? So if this number is a prime number, and then the other number is divisible by 3. It's just some statement consists of two shorter statements, right? So it's like this. And the last example is involve the word if and only if. So this phrase probably only appears in mathematics. In daily life, if you go to supermarket, you probably never use if and only if. Okay, so it says the quadratic equation of this x squared plus bx plus c equals 0 has roots. Real roots means has real numbers as roots. Right? If and only if, these are the funny words, if and only if this b squared minus 4c is bigger or equal to 0. Okay. Well, some of these statements are true, some may be false. I didn't claim these are all true. Right? If you are bored about these, you can think of which of them are true and why it's true, and which of them are false and why they are false. Okay? But these are the examples of statements which use some connectives. Okay. In high school or in JC, probably your teacher will tell you, will say what are the statements. So they will say statement is a English sentence, or is a sentence with truth value. You can tell whether it's true or false. So maybe it's better to give some sentence which is not a statement. For example, a question is not a statement, right? Say, just ask any question, right? So the question, there's no truth value. And the word is like go home. This thing is not a statement because there's no truth value. You cannot say whether go home is true or go home is false, right? But well, these are I don't know. I think we don't need to explain it anymore. Okay, so continue. So now we have seen examples. Now from these examples, we extract these connectives. So in the previous slide, the red words are not, and. Okay, there's either or, but in mathematics, usually we don't say the either. We just say the or. Okay. And this if then, and this if and only if. Okay. So now the atomic, the shorter part, we don't want to repeat it all the time. So let's use a letter to represent it. So usually we'll use P, Q, and R to denote a statement. And then we try to put P, Q, R together by connectives. Okay? And also the capital T and capital F, we use the two letters to denote true and false respectively. So these are, again, very natural. Right? Okay, so now we want to look at these 5 words. We study them one by one to see their so-called truth table. What are the effects they have on the truth? Okay, so first let's look at this negation, not, right? So we use this squiggle, this symbol, to denote negation of P. You may see in other textbook people use other notations. Well, it doesn't matter, right? So in this textbook, we use this stands for negation. So I'll read it as not P. Okay. So, for example, well, say the Earth is flat. If you take negation, the negation of the Earth is flat is the Earth is not flat. Right? So it's just like that. Okay, so use a mathematical example. So if P says this number, 331, is a prime number, then the negation, the not P, says this number, 331, is not a prime number. It's just add a not. Right? Now the impact it on truth is just flip the truth, right? So suppose, so here, this is an example of so-called truth table. So here, there's two statements, P and not P. And this table says when P is true, the negation of P, the not P, is false. Right? So the first row read like that, right? So if P, if the statement P is true, then the statement of not P is false, right? Well, if the statement P is false, then the negation of P is true. So this again is obvious. Okay, so that's the first connected negation, not. Okay. Now the second one is again very, very intuitive, very, very natural. You don't have too many concerns. Okay. So I want to so let's look at the property of this negation called and. Okay, so the mathematical symbol for this and, people usually write a wedge like this. Okay, so we use this wedge to denote the compound P and Q. Well, I don't want to say P wedge Q all the time, so allow me just say P and Q. Just read this wedge as and. Okay. Now the truth table for this, okay, so here, suppose you know the truth value of each component, that is, you know the truth value of P and Q, then the truth of P and Q is clear, is determined, right? So, so the truth value for P and Q is set this way. Only when both of them are true, P and Q is true, right? That's the meaning of and. Okay. Now, if one of them is false, then the compound is false, right? So if, for example, if P is true, Q is false, and then the conjunction is false, right? So I guess this again is very, very clear. Okay. So let's look at one example, right? Suppose let's fix a real number A. So the statement P says A is less than 4. And statement Q says A is bigger than 1. Then what is P and Q? So P and Q will say, okay, P, which is A minus A is less than 4, and A is bigger than 1, right? So you can write it in a shorter form, which is 1 less than A less than 4, right? So it's just like that. Now, okay, in mathematics things are clearer. In daily life, you may have some other words to say the same thing, right? For example, you can use but to, but this, okay, so let's see. So in everyday language, right, if we move away from mathematics, other words can be used for conjunction. Right? For example, this, he's rich but unhappy. So essentially it means he's rich and he's unhappy, right? It requires you know the meaning, and then you can use different words to express the same meaning. But most likely we are stay in mathematical world. I don't, although it's fun to analyze sentences like this. You will see some examples in the tutorial problems review. But those things are not, it's for fun, not for the study of mathematics. Okay. Okay, and then we move on to the next one. Any questions so far? Should be quite easy, right? So now we move on to the next one. The next one is, okay, there's one way to misread this OR. We will see, right? So we use this, okay, I'll read this as P or Q. This V to denote they call it disjunction of P or Q. Okay. Now the truth table for P or Q is set like this. If one of them is true, if at least one of them is true, the compound is true. So it's like this. So suppose both P and Q are true, then P or Q is true. And if P is true, if one of them like P is true, well, the compound is true. If Q is true, and compound is true. So in other words, there's only one case the compound is false, which is both P and Q are false, right? So let's see an example. Suppose P is A less than 4, and A is 4. A is a fixed number A. So the statement P says A is less than 4. Statement Q says A is equal 4. Now what is P over Q? So P over Q. P over Q is A is less than 4 or A is equal 4. Then we'll write it in shorthand as A is less than or equal to 4. Okay. Now, is this true? Is 3 less than or equal to 4 true? True, right? Because, okay, 3, we are checking whether 3 is less than 4 or 3 is equal to 4. 3 is not equal to 4, but it doesn't matter. 3 is less than 4. One of the compound is true. So in this case, the strictly less than is true. So then the OR is true, right? Now how about this one? Is 2 less than or equal to 2 true? It's also true, right? Because 2 is less than or equal to 2 says 2 is less than 2 or 2 is equal to. But, okay, 2 cannot be strictly less than 2. But however, 2 is equal to, right? So therefore, this compound is true because of the second disjunct is true, right? So both of these are true. Is this okay? Okay, now so there's one way to misread the mathematical OR. So this mathematical OR is called inclusive because when both P and Q are true, we still say P or Q is true. In daily life, sometimes the OR could be, they call it exclusive OR. It's like either you go or I go. Probably it means if you go, then I'll stay home. Right? So in daily life, things are not so how to say, so easy to analyze. So sometimes you have several ways of reading the same thing, right? In mathematics, the OR is inclusive OR. It allows both statements are true. Okay. Okay, so, and then from time to time I'll talk about two statements are logically equivalent. Right? Two things are, as far as the truth is concerned, they are the same. So sometimes we just simply say they are equivalent. So the definition is if the truth value in the corresponding rows of their truth table are identical. In other words, if you draw a truth table, how to say? Suppose I have one statement. I don't know, is P with some garbage here and Q. So this is one formula, and I have another formula P and maybe with some other garbage here and with Q, right? So for example, this guy may be P and Q and P, and this guy may be Q and P and P, right? Something is a statement about P and Q. Now, if they are equivalent, so here I will draw truth table. So the truth table is like this. So suppose I give you the truth value of P and Q. So say T, 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 T. And then in the first formula, you have a truth value here. Maybe this one give you true. And this one, well, if they are equivalent, it has to give you true, right? Now, you have another row. Maybe this is TF. This is TF. Now, if this guy give you F, then the other guy also give you F. So suppose you fill out the truth table, and it turns out the corresponding truth value are exactly the same. Then you say the two formulas are equivalent. I think this is intuitive, but somehow when you read the words, it sounds a bit complicated. But actually, it's extremely simple. I'll show you. Okay, so here's the example I'll show you. For example, P or Q and Q or P, they are equivalent. Because if you give P and Q the same truth value, and then both formula will return you the same truth value, right? So therefore, they are equivalent. They are not the same formula, right? If you look at symbols, the first one starts with P, second one starts with Q. But somehow, as far as the truth is concerned, they give you the same truth value. So they are equivalent. Okay. Similarly, P and Q and Q and P are equivalent. Okay. Now, okay, some people use this symbol for equivalence, but anyway. Now, why do we care about equivalence? So this is because if I have two equivalent statements, if I know one of them is true, the other one is automatically true, right? Because they have the same truth. So that's why it could help us. Okay. Now, the sentences could be very, very long. Sometimes there are several ways of reading it. To make sure that there's only one way, there's no ambiguity, we can add brackets. So let's see some example. For example, if I just write P or Q and R, so this is ambiguous, right? Because if I write P or Q and R, there are two ways of reading it. One is I combine P and Q first. It's like the second, it's like the thing here. I can combine P and Q first, and then take conjunction with R. So this is one way of reading it. I could also combine Q and R first, and then disjunct with P. So that's another reading, right? So why this is bad? Because these two are not equivalent. If I'm not careful, I write something like this, it will give you lots of trouble. Right? If I set an exam question, I ask you draw truth table of this, then you say, no, I cannot draw it because it's not clear what it means, right? So therefore, in this case, in the case of ambiguous, I have to add brackets so that everybody is clear about the meaning of the compound. Okay? There are other examples, so I will not read them all, right? But you'll know what I'm saying. Okay. Okay, so now we have seen three connectives, not and this and this or. What are the relations between the three? So let's look at some rules. So it's called De Morgan's law. De Morgan is a mathematician, is a logician. Okay, so he observed these laws, so it was named after him. So De Morgan's law. So the question is how do we negate P or Q? We are going to so we introduce some laws so that taking negation become symbolic manipulation. So we don't need to read the meaning, because sometimes reading the meaning was hard. If you can do it mechanically, just play with the symbols, life is easier. So we want to make our life easier. So we want to introduce some laws so that we can take negation without looking at meaning. Okay. So now how do we take negation of statement of this form, P or Q or P and Q? Well, so De Morgan told us this. The negation of P and Q actually is equivalent to not P or not Q. So you negate the two components, but you have to flip the connective. So the and becomes or, and similarly, the or you flip to and. Right. So this is the I think I don't have time to draw the truth table for these two, but I think you are able to do it. So if you draw a truth table, really you'll see that they give you the same truth value. Okay. Double negation. By double negation, I mean if you take negation twice, this is equivalent to P itself, right? So because you take one negation, you flip the truth value. You take it twice, then you flip back, right? So this is called double negation. Which is this? These two are equivalent. Okay. Okay. So then we look at some examples of De Morgan's law. So let's just look at one of them. Okay. So here's a statement which is a conjunction of two, right? So he is rich and powerful, and he is powerful. Okay. So we want to take negation, right? So what is negation? He is rich and he is powerful. So the answer was you have to take negation for each component and then connect them by or. So here's and, but you have to flip it to or. So the answer is, so he is not rich or he is not powerful. That's the negation. Okay. You can shorten it by neither nor, but that's an English exercise. Okay. Well, again, I'm worried about time, so I will leave these for you to read. So there are other examples of taking negations. So let me move on. I think there are things more interesting than this. Okay. So there are some other big words in the part of logic. So there's something called tautology. So a statement which is always true for all possible TF you give the component is called tautology. Tautology means always true. No matter how you let's see an example. So this is a typical example of tautology. So here I have not P bracket or P. I want to say no matter which value you give to the statement P, the compound is always true, right? Because if you give P true, then this is a disjunction. So one of them is true. So if you give P true, then the whole thing is true because of the second disjunct. Now suppose we try very hard. We want to give P false. Now the negation of P will be true. Right? So the compound is true because of the first disjunct, right? So P can only take true or false. No matter how hard you try, the compound is always true. So this is an example of tautology. Okay. And the opposite, the sentence which is always false, is called a contradiction. So the example is this: negation of P, not P and P. Right? P and not P cannot hold at the same time. Right? So there's no way this thing is true, no matter how hard you try. Okay. So this is called contradiction because it's always false. Okay. Now we are looking at probably the most interesting connectives. of the 5. It's called if then. Well, for those of you who are already trained by your teacher, this is not very interesting. But if this is the first time you see, it's interesting. Okay, so I pretend you don't know this. So let's go through this together. So we use P arrow Q to denote the compound if P then Q. And in a typical textbook, some people will say from P you derive Q. P implies. So there are lots of other ways of saying the same thing. Okay, so let's first see the truth table of P arrow Q. So when both of them are true, then P arrow Q is true. If P then Q is true, right? If P is true, Q is false, then there's something wrong, right? Because you start from a true statement, and then it implies a false statement. This is not good, right? So this is false. Now the last two was controversial. If P is false, and then according to this table, we set the truth value of this arrow to be true. Right. It doesn't matter what Q takes. As long as they call this premise, the hypothesis is false, the whole if-then, the whole compound is true. Right? So this is a counterintuitive, especially if you read P arrow Q as P implies Q, right? So if you read the historical books, you'll say maybe the philosopher Russell, people ask him that, if 1 + 1 is 3, then the moon is made of blue cheese, something like this. So according to the truth table, this is true. But what on earth, right? Why this kind of thing can be true? How can you derive from 1 + 1 is 3, derive the moon is made of blue cheese? So there are arguments of this. Well, the answer to these arguments, the shortest answer is, I set it this way, right? Don't argue with me. I have freedom I can set it whatever way I like, right? Don't argue. I set it this way, follow it, right? But obviously there are some reasons why you set it this way. So let's try. So, I'll say some explanations because these things are not, how to say. For example, if I give you this reason, and some people could give you example to support other possible setup, right? So these things are not proofs, not watertight proof, but it's just for fun, just to say that it makes sense. Sometimes it makes sense. So the first explanation is, this is probably the typical explanation. So consider, Singapore government actually said this, right? So if you get an Olympic gold medal, and then you get a certain amount, like $1 million. Right, so this is if then. If this, then that. If you are champion, if you are Olympic gold medalist, then you get 1 million. Now, when do you think it is true? The government keep its promise. And when do you think this is false? What we care is if you don't get, right? So the controversial part is P is false. So in the case, if you didn't get the Olympic medal, do you think this is true? The government keep the promise. I think yes, right? If you don't get the Olympic medal, how can you ask government, give me the $1 million, right? So if you didn't get it, the government doesn't need to do anything, right? So if P is false, we would think the government is still honest government. It keeps its promise, right? Only when the case that you really win the Olympic medal, right, and the government give you $1, then only in that case this is false. The government break its promise. Right? So this is an example to support the setup. Well, okay, so that's just a. Now there's other examples. Okay, so here this example, maybe we can use this as an exercise on truth table. So here is the suppose you look at this sentence. Do you think this is a tautology? Okay, suppose P and Q is true. Do you think Q is true? Yes, right? Because not only Q is true, P is also true, right? So P and Q is true. Certainly. So this is should be always true, no matter what happens, right? Okay, so if you believe me for that, then let's draw a truth table. So here I have P, here I have Q. So here I have my favorite P and Q, arrow Q. Now, just now I think you are happily agree with me. These four things has to be true, because the meaning of P and the meaning of this tells us it is always true, right? If P, right? So this says if P and Q, then Q. By looking at the meaning, if P and Q means both P and Q are true, right? And then Q is obviously true. So by looking at the meaning, this is always true, right? Okay, so no matter what happens, the last row has to be T, 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 T. Okay, so now let's draw the truth table. Okay, so it should be like this. Okay, now what is P and Q? This is true. This, you cannot see where I'm pointing at. Like the second row, so this is false. Right? This is false. This is false. Okay, so now look at the last two rows. So here I have F, right? Here I have F. Q is T. So this looks like F arrow T. It should be true. Sorry. If you agree with me, these things has to be true. Then there's no other way to assign the value, because you see here P and Q is F. Inside here, look at the third row. I'm looking at instance of F arrow T, right? Because this is F arrow T. So F arrow T, according to what we agreed, it must be T. Right? The same for this. Look at last row. This is an instance of F arrow F. Right? So you have to set F arrow F to be T. Otherwise, you can't get this. Right? Again, this is a, try to convince you, right? So here's another explanation. I'll tell you one more. I'll give you one more explanation after I introduce this double arrow. Okay. These things are, don't take it too seriously. It's just, right, I want to, whatever I say, I want to give you reason. Right, so this is my attempt to give you reason. Okay. Now, I already said some people will say that there are lots of other ways of reading this, because we use if P then Q. And then people can use something like suppose P then Q, assuming P then Q, given that P then Q. You have lots of other words to say the same thing. Or it's like it follows that. So P, because of P, it follows that. Or people use thus, therefore, hence Q. It all says the same thing, if P then Q. Okay, then you would see if the P arrow Q is true, then sometimes you have other names. So these are from historical reasons, because logic is an ancient study. So through the 1,000 years, people have lots of names for the same thing. Right? People say that P is sufficient condition for Q, and Q is a necessary condition for P. Okay. Now, there is a closely related connective. It's called only if or only. So here sometimes you see P, comma, only if Q. It means P arrow Q. Okay. So not the same as P if Q, right? P if Q means Q arrow P. Now, P only if Q means the P arrow Q. It is the opposite. So if and only if are the opposite pointing arrows. Give you opposite pointing arrows. So the example is this. So let's try. Right? So only an honest person can be a president. Or you can say one can be president only if one is honest. So this is P, president is P. This honest is Q. Okay, one is honest is Q. So this sentence, does it say P arrow Q or Q arrow P? So in other words, this sentence, does it say if one is president, then one is honest? Or it says if one is honest, then one is president? It only says if one is president, then one is honest. Right? So it's P arrow Q. Okay, so I can give you an explanation, right, using Venn diagrams. Let's say that P denote he is a president. So he is someone. Okay, one is president. And Q says he is honest, or he or she, he is honest. So now the question is, so here I have a collection of P. So this, I use Venn diagram. This circle denote the president in the world, right? The collection of president. Now here I should have another, okay, so I draw it somewhere. I should have another set or another collection of Q, which is the honest people. People in this circle will be those honest person. Now, what is suppose I have this. Only an honest person can be president. What are the relation between P and between these two circles? Should it be like this? P is here, Q is there. Or should it be like Q is here, P is there? Right? So this is our question. So here it means P arrow Q. Now this part means Q arrow P, right? Sorry, I'm trying to say this. Imagine, let's use P to denote the set of precedent, the collection of points which has the first property. And then the Q denote the collection of people being honest. Okay? So now we want to decide whether this sentence says P arrow Q or Q arrow P. Now what's the Venn diagram for P arrow Q? Means P is sitting inside Q, right? Okay. The Venn diagram for Q arrow P means Q is sitting inside P as sets. Okay. Now what do you think? Okay, so let's draw Q first. So Q is here. Q, remember Q is the honest person, right? Honest person. So now this sentence, one can be president only if one is honest, means anybody outside Q has no chance to be president, right? So in other words, okay, so here is all the human beings. It says if you are in the shaded area, you have no chance, because only the people being honest has a chance. So if you are outside the honest circle, you have no chance, right? So therefore, the picture must be P is somewhere sitting here, because inside Q, maybe there are lucky people with being president, right? Or it doesn't mean everybody honest will be a president, right? I think everybody in the classroom is honest, but I don't think we are all president. Okay, right? So this is a explanation why the only if means this way, means P arrow Q. Again, let me emphasize, these things are my explanation. You may buy it if you have better ways to understand this. By all means, do it in your own way. But you have to interpret in this way. You cannot give a new interpretation. Right? You cannot give a new truth table. You have to give this the same truth table. Okay, so again, the brackets are important when we have this connected. For example, even this P arrow Q arrow R is not equivalent. So you first bracket P arrow Q, then arrow R. It's different from you first have Q arrow R, then add a P. You can, I guess, I suggest you draw truth table of these. This is less obvious than the and or example. This is a, please draw truth tables and see how it goes. Okay, so therefore, if you write this, it doesn't make sense. Unless you say, when I write this, I mean that. But if you just write this, I don't understand you. Okay, so here we try to establish the relation between these connectives. Actually, also with negation. Negation. Okay, so if you just have negation and or, actually you can express P arrow Q in an equivalent way. So the claim was P arrow Q actually is the same as not P or Q. And it's the same as this. It's not the case P and not Q. Should we practice? Okay. So let's draw truth table together. So here's P, here's Q. I have T, T, F, F. I have T, F, T, F. And then I have P arrow Q. I'll do one. I'll do one simple comparison. 1, 2. Okay, so this for P arrow Q, by our convention, we'll have this. Right? We have set rules saying only in this case, P is true, Q is false, this is false. All other cases is true. Right? Now let's look at this. Is this column also read as TFTT? Well, if Q is T, then this one should be T. So at least I know the first and the third row has to be T because Q is T. Now look at the second row. The second row, when P is T, negation of P is false. So I'll have false or false. So I have false here, right? For the last row, when P is false, negation of P is true. So the OR will be true. So I also have TFTT. So comparing these two columns, they are exactly the same. So therefore, these two statements are equivalent. Okay. I will not do this during the lecture. You can try it. It's equivalent. Okay. Now, how do we take negation of if then? This is equivalent to P and not Q. Well, I'm sorry, I didn't do 3. So if these two are equivalent, taking negation for 1 is like taking negation for 3, right? But then I would have a double negation. So these things are canceled. I have exactly P and not Q. So, for example, the negation of if X, okay, so here's some example. Okay, so we want to have more examples about spend a little bit more time on if then, right? Because sometimes people make mistakes and so on and so forth. So so let's start from here. So the statement Q arrow P is called the converse of P arrow Q. If you flip the premise and conclusion, you'll get something called a converse. Okay. For example, if P, let P say A is less than 1, Q says A is less than 100. So what is P arrow Q? P arrow Q means if A is less than 1, then A is less than 100. Okay. Now what is its converse? The converse says if A is less than 100, then A is less than 1. Okay. Are they equivalent? No, right? Because P arrow Q in this example is true. If A is less than 1, then definitely it's less than 100. On the other hand, if A is less than 100, it could be 99, right? Which is not less than 1. So we cannot say if A is less than 100, then A is less than 1. So the converse is false. So a statement and its converse are not equivalent. Okay. Right. So okay. There's another related word. So the statement of not P arrow not Q is called the inverse of P arrow Q. You just take the negation of both components. So for example, let's look at the example, right? So P arrow Q says if A is less than 1, then A is less than 100. Now what is the inverse? It says if A is not less than 1, then A is not less than 100. Right? But this is not true because 99 is not less than 1, but 99 is less than 100. Right? So therefore, the inverse and the original statement are not equivalent. Okay. Okay, then the textbook is talking about converse error. Right? So from the above example, we know the statement and its converse may not be equivalent. Okay. So if you make mistake by messing these two up, you are committing an error, logical error, called converse error. Okay. For example, here, so the statement says, if it rains, then I bring an umbrella. The converse says, if I bring an umbrella, then it rains. Right? So are these two the same? If you think these two are the same, then you are committing a converse error. But these two are obviously not the same, right? And same, you can have a mathematical example. I guess I have to speed up a bit. Okay. Now, we have seen the converse inverse. The last possible variation is called control positive. So the statement not Q, arrow not P, is called the control positive of P arrow Q. Okay. And it turns out P arrow Q and its contrapositive are equivalent. You can draw a truth table. Okay. So look at the same example. P arrow Q says if A is less than 1, then A is less than 100. What is the contrapositive? It says if A is not less than 100, then A is not less than 1. Okay. So that's the contrapositive. So similarly, converse and inverse of a statement are equivalent. So it says this. So originally you have the original statement is P arrow Q, right? So here you have its converse, which is Q arrow P. Now here you can have its inverse, which is not P arrow not Q. The last part is this contrapositive, which is not Q arrow not P. So what do we know? We know these two are equivalent, and these two are. Can I change color? Let's change it to red. So these two are equivalent, and and these are not equivalent. Okay. These are not equivalent. Same. These two are not equivalent. These two are not equivalent. Right. So among the 4 variations, the diagonally they are equivalent, but all other pairs are not. Okay, so now I'm going to introduce the last connectives in logic. This is the if and only if. So we use a double arrow because you have seen if, then you have seen only if. Just put them together, you get if and only if. So the truth table means the P double arrow, some people call it biconditional. So this is true only when P and Q have the same value, right? So if P is true and Q is true, then this double arrow is true. If P is false and Q is false, the double arrow is true, right? When they have the same value, the biconditional is true. If they have different values, then this double arrow is false. Right? So this is easy to remember. As the name suggests, right, P double arrow Q is the same as if P then Q and only if. Right? This part stands for only if. So therefore, this double arrow is reads as if and only if. So these two are equivalent. Okay. In mathematics, people usually use IFF as a shorthand for if and only if. Your spell checker always say this is not correct, but people in mathematics use it. If you have this double arrow, then P is a sufficient and necessary condition for Q, right? As we said before. Now here I can give you another explanation of why we set up this P arrow Q truth table like TFTT. Okay. Now here, I want to convince you that suppose we hate the way we set up, right? We don't like it. We are unsatisfied. We don't like it. So we want to do it our own way, right? So we want to draw a truth table of this in our own way. Okay. But I guess the first 2 rows is less controversial. People would agree with me that if both P and Q are true, P arrow Q should be true, right? If the first one is true, second one is false, it should be false. These 2 things, I hope everyone agrees with me. Now the only choice we have, only controversial part, is the last two rows, right? So we set it in this way. We set it TT. And now we really don't like it, right? So we hate this. So give me your option. If you don't like TT, what can you have? So you can have TF. You can have FT. You can have FF. Right? These are all possibilities. Now, are we happy? Is this better than this? Now, suppose you set it like TF. Let's look at this option. It turns out the truth value P arrow Q is exactly the same as Q. You see, Q is TF, and here is TF. You don't want the if-then only depend on Q, right? It has nothing to do with P. It's not good, right? So this has some problem, okay? Now how about this? I set it as TFFT. Now this is the same as double arrow. You see, the double. If you still remember the double arrow, when they agree, you give T. When they agree, you give T. When they disagree, you give F. So, well, it's better to have a double arrow for double arrow, right? So double arrow shouldn't play the role of this single arrow, right? So therefore, this has some problem. Now, how about the last one? I set it as TFFF. Now, this is exactly like a OR, right? Because when both, like AND, when both of them are true, if one of them is false, you get false. So this is like AND. Now, if-then shouldn't be the same as AND. Again, this is not ideal, right? If you believe this, then it seems this is the only choice. Well, again, you don't need to buy this, right? It's just I'm trying to convince you. Okay. All right. So now we in the agenda of today, we have three things. One is introduction to logic. The second one is connective. The third one is logical rules. So here is the last topic, our last topic, about logical rules. So intuitively, it is clear that if you have, okay, P arrow Q and P, you can get Q. This is some derivation, right? So this derivation, it should be true. Right? So from these two, you get Q. Okay. We can set it as the so-called inference rules. So we can set it as a logical rule for us to generate more and more statements. Okay. And it has a funny name called models podent. So observe this rule preserves truth. If this P arrow Q is true and P is true, and then Q cannot be false. Because if Q is false, then this one is true. Right? So this one is false. So if the first two are true, there's only one possibility for Q. Q has to be true. So therefore, this preserves truth. Okay. Okay, now, so we have one rule. So the rule says from certain hypotheses, you can get something new. So this is an example of a rule. So suppose you have first two, and then you can do something, you can get the last one. So you can do one step further. So this is a rule, right? So we don't want to, we cannot give a precise definition of logical rules. But in this course, very often we are going to use some rule. So the rules we are going to use are usually coming from the tautology. So let me give you an example. Right? So here, this is another example of rule. So from P arrow Q and Q arrow R, we can get P arrow R. Intuitively clear, right? suppose you give me P, how do I get R? So if you give me P, I can get Q. And then from Q, I can get R. So of course, from P, I can get R. Right? So this is a rule. Now, how do we justify the rule? Because this is a tautology. So these things keep truth. So this is this tautology justified of making this as a rule. Well, I don't think we are going to use lots of complicated rules. So let me skip some of these. Okay, so now I want to give you an example of a proof. Right? At the very beginning, I said a proof is a sequence of logical. It's a sequence of reasonings, and each step is by a logical rule. Right? So let's try to see example of proof. So this example is the first example of the statement. So there's a funny number. I claim this funny number is not a perfect square. Okay. So this funny number is too funny, so let's call it Z. So that. Now, I didn't explain what is a perfect square. A perfect square means this number is a square of another integer. For example, 4 is a perfect square because 4 equals the square of 2. Right? 7 is not a perfect square because 7 is not a square of anything. Okay? So perfect square means you are a square of an integer. Okay. So we want to say this Z is not a perfect square. So how do I prove? How do I show it to you? By the way, this is an example of something called proof by contradiction. This is a typical mathematical proof. So maybe we can use brute force, right? But this is too tedious. What do I mean by brute force? You just check all possible numbers, right? You start from 1. Is 1 square equal this? Is 2 square equal this? 3 square equal this? You try until you hit this number. If none of them equal this, then it's not. But of course, we don't do that, right? Even with a helpful computer, we don't want to do that. Okay. So now, so maybe this guy is indeed a square. So maybe this guy is t, is t squared, right? So now let's try to reason, right? Let's try to say. So what can we say about t? Suppose if z is t squared, what can we say about t? So the first thing we can say about t is t must be odd. Odd means cannot be divided by 2, right? Even means divisible by 2. Do you see the reason? So z is like this. Can it be a square of even number? No, right? Because the square of even number is even. Now this funny z is not even, so it cannot be a square of even number. So t must be odd. So now let's look at the property of odd number. So the odd numbers are the ones end with 1, 3, 5, 7, or 9. Right? So that's all possibility. So if you write an odd number, the last digit has to be odd. Has to be like this. Okay? So if t ends with this, t squared, the last digit of t squared will be 1. And then if it ends with 3, the 3 squared will be 9. Right? If it ends with 5, 5 squared, 25. The last digit is 5. If t ends with 7, 7 squared, 49. The last digit is 9. Right? And this is 81, give you 1. So if t ends with 1, 3, 5, 7, 9, t squared should end like this. Okay? Why is that? Because when t ends with a 1 means you can write t as a multiple of 10 plus 1. Right? let's say t ends with 1. So let's say t is, okay, 1001. Okay, so I can write t as 1000 plus 1. So this is 100 times 10 plus 1, right? So you can see this will explain if t ends with something, you can write t as 10 times something plus 1. Okay. Now when you square, again, this part is 10 times something. So it is from, how to say, this part only have something to do with the second to the next integer. It has nothing to do with the last integer. So therefore, t squared will end with 1. Okay, now we can, by this reasoning, we know this z is not a perfect square, right? Because it cannot be a square of even number, and it cannot be a square of odd number. Because if you are even, the square will be even. If you are odd, the square must end with 1, 9, and 5. But this funny guy ends with 7. So it cannot be a square of even number, it cannot be a square of odd number, it cannot be a square, right? Okay, so now, so here's, in math department, people write these things, right? So here's a proof, right? So suppose the given number z is a square of some odd integer t. Now t has to be, because it's odd, t has to be 10 times m plus r for some integer m and for some integer r. The r comes from the list 1, 3, 5, 7, and 9. So then t squared will be this in this form, right? So therefore, the last digit of z, which is t squared, is the same as the last digit of r squared. Now r squared, we just calculate, is either 1 or 9 or 5. So, but z's final digit is 7. So therefore, z cannot be a perfect square. Okay. So let's make some comment. So we take a closer look at the proof. So the proof begins with, suppose this is a square. So this is the contrary of what is claimed, right? So we want to show this guy is not a square, but we begin with, suppose it is a square, right? And then we get, okay, so why do we start with this? Okay, so the one advantage is it gives us something to work on. Suppose it's a square, which is t squared, then we work on t. So otherwise we don't have anything to work on. So we then deduce that if this is a square, then you get some funny contradiction, right? So because of this contradiction, we have to admit our assumption, our supposition was wrong, right? In other words, this supposition was wrong. Assuming z is a square, this thing was wrong. So z is not a square. So this is an example of proof by contradiction. Next week we are going to see more examples of proof by contradiction. Okay. So this kind of argument, assuming what you wish to prove is false, and deduce a contradiction from this assumed falsity, is commonly employed in mathematical proof. This is called proof by contradiction. In the later part of Living with Math, sometimes I'll give you some proof. It's optional. You are not required to know proof. But in the proof, very often I have to use proof by contradiction. So that's why in the first few lectures, I want to make this clear. Okay, so summary for today. So we have introduced 5 logical connectives, these 5. And then for a compound statement, we can draw truth tables, right? We know how to draw truth tables. And tautology is a statement of what is always true, right? Now, okay, I still have 3 minutes, so I want to use the 3 minutes to tell you to give you a big open problem. Okay, so this is optional. You don't need to know. So now we want to say something interesting, but it's not in our syllabus. So here is a problem called SAT. So it's called satisfaction. Right. So the problem says this. I give you a statement. You have to decide whether it's a tautology. For example, I give you a statement like this. P or Q and R, I don't know, this thing, or not R and Q. So I give you some statement like this. You tell me whether this is tautology. Well, you can tell, right? So the most natural algorithm to decide whether this is tautology is you draw a truth table. You draw a truth table, then look at last column. If always true, then it's tautology. Otherwise, it's not, right? But this usually, if a statement is of certain length, say length n, the truth table you have 2 to the n many rows. There are lots of combinations because right, true, false, true, false. So there are. Suppose you have P and Q, the truth table is there are 4 rows. Right? If you have PQR, the truth table will have 8 rows, which is 2 to the 3, right? So the algorithm, suppose you just use truth table to determine whether this guy is a tautology, the algorithm is of exponential growth, right? When you have longer and longer formula statement, it takes longer and longer time to decide. Right? So the question is, can you do better? Is drawing truth table the only way to decide it? Is there an algorithm which is faster? For example, is polynomial growth. Right? So this is okay. So this second, the last line says, is there a polynomial time algorithm which determine whether a statement is a tautology? So that's the question. Okay. Sounds very innocent, right? Sounds like you can do it. Maybe you can. Right? But this is one of the 7 millennium problems. So at the turn of the millennium, there are 7 famous mathematical problems. The problem I just stated is a way of saying something called P versus NP. P is for polynomial time algorithm. NP is for non-deterministic. I don't have time to explain what. Maybe by the end of the semester, I have time to talk about Turing machine. I'll tell you what exactly it is. But anyway, so the one statement, one way to phrase this P versus NP is this statement. Is there an algorithm of polynomial growth which determine the set problem? So that's the question. So the set is a typical problem in NP. So the question asked is P equal NP. So now we are going to have Chinese New Year, right? So if you have nothing to do, try this problem. If you solve the problem, no matter how steep is the bell curve, you get A+. Okay, so the last paragraph. So what is, in layman terms, why the problem is hard? Right. So here's the reason why the problem is interesting. So usually you have okay. Okay, suppose you see a problem. They are to solve a problem and check the solution is correct are 2 different things. Sorry, I give you a problem, you solve it, or I give you a solution, you check whether the solution is correct. These 2 problems are of different nature. You can imagine that checking a proof is much easier, right? It's like I grade your homework, or I have to come up with a solution myself. Grading, I think, is easier. Just check. If you have a mistake, you're wrong. Otherwise, it's correct, right? Now, if you ask me to find a solution, I don't know where to find. So it's lots of hard work. So these two things are different. But this P versus NP problem is like this. So the satisfaction problem is easy to check, but difficult to solve. Now, if you can show P equal NP, it means you have a clever way of reducing solving the problem to checking the problem. So therefore, it's a fantastic thing, right? On the face of it, solving a problem is much more difficult. If P is NP, if you are able to show P is NP, and then solving a problem is more or less the same as checking the solution. So most people will guess that P is not NP, but they are unable to show it. So there's still a chance that P equal NP. So well, during the Chinese New Year, you can try. So let me repeat. We'll have no lecture on Friday. Okay. Starting from next week, we'll have tutorials. I already upload the tutorial problems on the website, right? So please get it from there. Okay. So Happy New Year. Okay. See you next week.
Therefore, we can already know that within the bigger Venn diagram, that means that if it's P, it's going to be Q.
Yes.
Then, what I know is for the discussion, which is Q is the compass, right? Correct?
Yeah, you can say that.
So if we say Q is a P, that means that if Q is under the bigger umbrella